Hi, my name is Simeon Withier, and I am a first-year PhD student here at UCCS studying cybersecurity with my advisor, Dr. Sang-Yoon Cheng. I will be presenting my work titled A Proof-of-Work Network Simulator for Blockchain and Cryptocurrency Research. This is a demo paper that was accepted into the IEEE International Conference on Distributed Computing Systems, also known as ICDCS, and this work is supported by the National Science Foundation under grant number 1922410. So to get started, I will discuss what peer-to-peer is and how this technology has sparked a new area of research in securing the communication between users and moving away from centralization. So essentially what it means for a system to be peer-to-peer is that it is community-driven, where every node acts as both a client and a server. Unlike traditional scenarios where every user or client relies on a central authority or server to ensure the synchronization of information. Peer-to-peer completely removes the centralization so that nodes connect to one another and information is verified and propagated in a flood-based manner across the entire network. So the great thing about P2P is that it's resilient to service outages, bad actors, selling user data, and various attacks, for example, intrusions or viruses, data corruption, malicious insiders, and denial of service attacks. Similarly, proof of work, also known as PoW, is an incentive mechanism and consensus protocol where nodes all work in unison to solve a globally distributed cryptographic challenge. While yes, it is computationally intensive, it also guarantees that any solution or proof is genuine and that the solver can prove that they did indeed solve the challenge so that they can receive the reward. This is known as zero-knowledge proofs, and the PoW consensus protocol basically says that you want to store the most recent block in memory, where a block is just the data for some transactions, and you guess a random number repeatedly until the hash of that data is within a certain numerical threshold, also known as the difficulty. So hashing is a one-way function, and what that means is it's quick to compute, but it's very difficult to reverse. So after you run it through the one-way function, you check that if it's a block or if it's a valid block, and if it is, then you can submit it to your peers for a reward. Otherwise, you just simply repeat the infinite loop and guess another random nonce. So you have the system where nodes all connect to one another and are constantly mining to increase the blockchain for a reward. But how do you know that the system is working properly? Well, the short answer is you don't. If you have 6 nodes and each one maintains 2 other random connections, then it's possible that there will be a broken network, i.e. not every node is reachable. Therefore, 2 separate blockchains will exist that are independent from one another. And I visualize this by showing that the blocks from each network partition in this are in separate colors to the left and to the right of the node topologies. Now, the problem comes when a new node joins the network. Let's say that the partition network suddenly becomes connected, then which chain becomes the main blockchain? Well, the proof of work consensus protocol says that you want to select the chain that has the most blocks on it. But this means that the network has just lost the blocks from the other blockchain, meaning that all the computing power that went into solving and verifying the correctness of those blocks was completely wasted. So then you may be thinking, what if the nodes maintain a higher number of connections? Well, yes, that will fix the disconnected network problem, but now this introduces a new problem. It means that there's more overhead in transmitting data between the nodes. So if you want to understand the network and simulate the scenarios previously discussed, and maybe even take some measurements, then how would you do this? There's plenty of parameters to vary. So what about the connection latency, or the rate that blocks are solved, or the bandwidth to upload and download information, or the block size, or the network propagation time, or even the topology of nodes? Say you want to measure a specific topology with connections in a certain order, then how would you do this? Well, as you may know, the peer-to-peer and proof-of-work concepts that I discussed previously are a part of Bitcoin. So if you wanted to connect research on them, you could connect multiple Bitcoin instances to one another. And this could be done with either many computers or many virtual machines. However, computers are expensive in terms of money and physical space, and then virtual machines are expensive in terms of CPU and memory usage. So my work aims to help with the preliminary measurements and modeling of networking scenarios before having to implement them in the real world with real blockchain instances. So I call it the blockchain simulator. It's a web application built in JavaScript. It's easily accessible and assists in blockchain related research. So here is the URL to access it, and I'll post it in the discussion. All right, and I'll briefly demonstrate the simulator to make it more interactive, and feel free to experiment with all of this yourself. All right, so here it is. Here's the blockchain simulator. We have the file tab where we can save the network to file or to local storage or to the clipboard, and you can load it as well. So that's really useful for if you want to save your work and things. Here's the GitHub repository. So like if you want to look at the source code yourself, you can. Feel free to. Everything is readily available. Yeah, and then there's the network. So this is for if you want to add or edit miners, remove miners, change any parameters about the miners and whatnot. There's topology for all the connection data if you want to modify the actual topology, and then display for if you want to toggle things. So like if you want to remove the visualization, now this saves a lot more computing power on the page as opposed to enabling it, which is useful for larger networks. And yeah, so here's the list of nodes. You can select them. Every node has a different color associated with it. And then here's the editor. So if, like, let's say node 14, we can modify the computing power to 3 hashes per second now. Things like that. And here's the bandwidth, download rate, upload rate, all those kind of things. You can see like incoming peers and outgoing peers is all there. Which it's a little bit cryptic to look at, which is why there's also a visualization of the network. And so you can like look around, you can modify things, you can see clearly if there is a disconnection in the network or things like that. Every time you refresh the page, it generates a new random network, random parameters and things like that. So for the topology, if you wanted to generate a new topology, you could. So let's say like a ring of 10 nodes or something, you can do that. And let's say we want to start the miners. Every time that a block is found, it appears as a black dot for a short amount of time. So you can see actually the blocks propagating through the network. And then here's a time plot of that data as well. So you can see exactly when the nodes find it. And you can change the time plot to whatever you want, like network buffer, which is essentially the router data. Not sure how useful that is, but you can you can visualize any part of this simulator and visualize it and show what's happening, which is kind of useful. And then right here's the table for all of the miner data, like number of accepted blocks found or number of rejected ones and whatnot. And then here you can actually sample the data. Like every 20 seconds we'll sample the data, we'll run this in the beginning, and you can program in, this is JavaScript, you can program in your own logic into the simulator to run, and you can log the data, choose all the parameters you want, and yeah, that's about it. So yeah, feel free to experiment with it. It's this URL, and yeah, thank you all for watching. And if you have any questions, feel free to post them in the discussion board, and I hope you all have a wonderful day.